So yeah, I'm talking about bioactive molecules on the as active materials, electrolyte materials for redox flow batteries. Redox flow batteries are necessary for large-scale energy technologies, and there's need to diversify these battery chemistries because of future resource constraints, and hence it is central to the global drive to achieve net zero emissions. And then you have this schematic here of what the redox flow battery looks like. The conventional batteries that we know, we have the anode and the cathode as solids. But in redox flow batteries, we have the anolyte and the catholyte as serving as the anode and the cathode respectively. And then you have a pump that pumps this electrolyte that assists in circulating the electrolyte through the system. And energy is produced by transfers of electrons within the circuit. But within the cell, there is also the movement of ions as well. Redox flow batteries are viable and they are low-cost battery technologies for use, especially in developing countries and emerging economies. In redox flow batteries, power and energy can be decoupled. So it depends on what you are interested in. You can decide to increase the amount of electrolytes so as to increase the power capacity, or you can decide to increase the cell, the volume of the cell in order to increase the energy density. So redox flow battery is scalable, though the energy density, specific energy density is not as high as that of the lithium-ion batteries. But for grid scale application, the energy density still falls within what is acceptable. Now, there are different electrolytes for RFBs. You have the iron chromium, vanadium, all vanadium, zinc bromine, hydrogen bromine. But my focus is on the organic electrolytes. And then for the organic electrolytes, why organic electrolytes? They are nature's organic electrolytes can be obtained from nature because nature is the chemical house of these molecules, and also they are renewable and environmentally friendly. And these organic molecules possess heteroatoms which are abundant in the earth crust, like carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus. And another very beautiful thing about them is that they are tunable. Like the molecules here, all these points, these points of unsaturation here, the heteroatom here, the oxygen you can see here, these are active points, and they are reactive, they're centers of reactions and electroactivity. So for a good electrolyte for redox flow battery needs to be soluble. It needs to be soluble in the solvent that is going to be using, because for you to have an electrolyte, you need a solvent, and you need also a solute. A solute could be solid or a liquid, but you need that solute to be soluble. And the electrolyte needs to be stable. The compound they are using, the solute has to be stable, and it needs to possess redox properties. Vanadium redox flow batteries, or the vanadium redox chemistry, yeah, the battery has been established already and has reached the point of commercialization. But then there is need to come up with the organic ones, the green molecules, because they are safe and low cost, and then they are sustainable because they are found in the earth crust compared to vanadium. The cost of vanadium is high, and also the vanadium ion in its high oxidation state is toxic to the environment. It's harmful to the environment. So I worked with the Gray group in Cambridge, and then we were looking at some of these organic compounds from plants, bioactive molecules, and then we looked at quercetin, which is a polyphenolic secondary metabolite of plants. It's also a kind of flavonoid. And then the overall oxidation mechanism in quercetin involves 2 protons and 2 electrons. We don't need to start getting all the apples in the world to get quercetin, but we can get these molecules from plant waste. And the technique for doing this, you have to characterize it by subjecting it to physicochemical analysis. That is the solubility test, the viscosity test, and the conductivity. And then you also need to carry out chemical and electrochemical characterization using a cyclic voltammetry, galvanostatic cycling, so as to establish its redox properties, its electrochemical stability. And then you need to carry out NMR and EPR studies so as to understand in details the molecular or atomic behavior of these biomolecules when they are present when they are acting as electrolytes. In the case of quercetin, we discovered that it was it was not so soluble in aqueous solvents. The solubility in an alkaline solution, that is potassium hydroxide, was just 16.54 millimolar, but we observed it was so soluble in DMSO, which is an organic solvent, and some of these bioactive molecules have that problem of being more soluble in an organic solvent. However, there are some that are soluble in aqueous solvents. This is the NMR spectra of quercetin in DMSO. You can see it is very clean with all the peaks of the protons coming out clearly, meaning there is no degradation. And then, however, the cyclic voltammetry of quercetin in the alkaline solvent, that is potassium hydroxide, was not very good because there was no electroactivity seen in it. It was rather undergoing oxidation. That's a kind of instability, degradation, sensitivity to air. You can see on this graph here, there's no the graph left, the voltammogram by the left, there's no sign of any electroactivity. And the voltammogram on the right, you can see it's just basically oxidation that is taking place. Sorry, the slide is a bit, is freezing a bit, but I'll see how I can go through this. I'm sorry about this. Sorry about this. Oh, I'm so sorry about this. Can you see my slides?
Yes, we can still see, thanks.
But I'm sorry, this is freezing. Maybe it's because of the programs, the software that I used.
Do you want to close it and start again?
Okay.
And just go through until you get where Should you get back?
So like I was saying about the organic redox flow batteries, they are subject to degradation when exposed to air. And then, but the good thing about this is that because of their molecular structure, they are tunable with the presence of the heteroatoms and the conjugations in them. They are tunable, so they could be molecular engineered to have desirable properties that will make them to be soluble in aqueous solvents, and then to have the desirable electrochemical properties. So at the lab at Cambridge, at the Claire Gray's group there in Cambridge, I was able to look at some bioactive organic molecules like quercetin, flavin adenine dinucleotide, and then flavin mononucleotide as well. And then these molecules appear to be promising. And then further work could be done on them by carrying out molecular engineering so as to prevent degradation of the molecules and to make them to have more desirable electroactive properties that will make them to be useful, very, very useful in the applications in redox flow batteries. Already other molecules have been patented, organic molecules that have been, there are organic molecules that have been patented as electroactive molecules in redox flow battery applications, like some of the anthraquinone molecules. So it's worth exploring these other molecules in plant materials, like the polyphenolics and the flavins, so as to enlarge the database for these organic molecules as electrolyte materials for redox flow batteries. Thank you very much.
Thank you, and well done continuing despite that. It's we haven't got enough time for another presentation, and I'm not sure if we've got somebody who should be presenting in the audience. So what I'm going to do is ask if anybody's got any questions from those or on those who've already presented, because we've got about 8 minutes before we should go for the break. We took the break early, but let's see if there's any questions. Thank you. Well, I've got a question for Sandili. On your presentation, when you showed the XRD results, there was quite a high background. Is there a reason for that? Thank you.
Yes, Prof. You mean the? Oh yes. The reason for that, I think it may be attributed to the. I think we had didn't have enough powder samples for that, but yeah, I think so. I'm not really sure actually. Yeah, but I think that might be the reason, as it also showed on the absorption. Absorbance spectra as well.
Thanks for that. I was just curious, and thanks for the honest answers. Thanks. Are there any more questions? I have a question for the last speaker. I'm glad you said that you get your plant material from plant waste, because I was worried that it would be sort of compromising a food source. Are there any particular things you have to do to get your to the plant waste? Thank you.
Hello. Can you hear me?
Hello, I was asking you a question.
Yeah. There are things that need to be done And that's where it calls for collaborations with the organic chemist. The molecules have to be isolated. And those in natural product chemistry also collaborate with us, and then we isolate those molecules and then carry out this experiment. But the good thing about it is that with molecular design, they could be obtained in commercial quantities, and then they can as well be used for this application. Does that answer your question?
Yes, it does. Thank you very much.
Thank
and
you.
thank you again for pushing on with your presentation.
Can you see my slides now?
I can now, but if we, what do you want to do? Because
no, just run through the slides.
Okay, but where were you? Because I thought I'd asked you to take your presentation through to the end.
Yeah.
Apparently Bertrand's shown raised hand. So if you'd like to, Bertrand, sorry, if you'd like to answer your question, ask your question, please.
Hello, can you hear me?
Yes, I can hear you.
Okay, so my question was to the last speaker. Thank you very much. So I was going to just ask what Prof. Leslie was asking. How do you go about doing the treatment for your the material you get from the waste? I mean, the molecules, how do you go about doing the treatment when you get your waste? And then I also wanted to find out in just about how much quantity would you actually get your bioactive molecule, and on a commercial basis, is that really going to be, well, I don't know, commercially sustainable, or well, not sustainable, but in terms of mass supply, would that be a viable way of trying to produce the organic electrolytes? Then I think the last question I had with that was, how do you ensure that you don't have a mixture of
Thank you for the question, Bertrand.
Because
about the isolation processes, I'm not an organic chemist, I'm an electrochemist. And that's the work of the organic chemist, the isolation processes. But I know it has been done before. And then talking about the quantity, there are waste everywhere. The focus is that this is environmentally friendly. These molecules are not harmful to the environment. That's the emphasis. They are benign to the environment. They are not toxic to the environment. They can be designed with this in mind. Just like you have your paracetamol, you have your quinine. You don't go to the plant today to go and start getting them synthesized. Those people that are in that field of chemistry, they know what to do about it. But the emphasis is that it's environmentally friendly. So for this work, I did not go to get some waste to isolate the quercetin. I only had to buy, I placed an order for it. It was obtained in commercial quantity, and I was able to do this work. I don't know if that answers your question. Hello?
I was just actually done something, so at least I see that you see that you worked on quercetin. I wish you could have presented the results also, that we see what you got.
The result of?
Oh yeah, I did see something. I saw something on that. Yeah.
Hello?
Okay, no, it's fine. Did you hear me?
I didn't get you.
Okay, no, I was just saying that I was just wondering whether you were still just at the planning phase or whether you actually did experimental work. But from your mentioning of quercetin, and I see one of your last slides you did just before you went off, or your slides got froze. I see that, yeah, you did do some practical work. Yeah. So now the question, maybe I'll ask one last question. How did you go about the modification? Or that was the organic chemist work? Let me read that, yeah.
This is a preliminary study. The modification has not been done. This is a future work.
Okay.
What we obtain from the present, what we observe from the present work is that the molecule is degradable, is sensitive to air.
Mm-hmm.
And so what we can do about it is to modify, be able to improve the solubility and stability, and then carry out long-term cyclic voltammetry to look at this, to examine its solubility, its electroactivity, or its electrochemical stability.
Okay. Yeah, thank you, Habibat, thank you. I get an idea of what's happening.
Thank you very much for now.